from chapter 6. All right. So, what we're starting today is chapter 5. Chapter 5 will be the last chapter we are covering this year. Rational exponents and radical functions.
I have a question, Mr.
Yes.
Are we going to do like a final, or is this going to be one of our regular tests?
This is going to be one of our regular tests. Most likely this is going to run all the way up till the end. All right. Now the first thing we're looking at is this here. Which is going to be greater, the square root of 64 or the cubed root? Cubed root of 64.
Yeah.
Now what is?
It's the square, no, the square root of 64.
Square root of 64 is 8. Because when we look at a square root, we're saying what times itself is the number inside. So 64, square root of 64 is 8. Cubed root of 64 is 4. Because we're trying to figure out what times itself. 3 times gives us 64. And we can do this in a calculator. We can see what 8 squared is. It's 64. And then we can do 4 to the third. It is also 64. So square root of 64 is going to be bigger because we're trying to find, in this case, square root of a number. We're trying to find a number times itself. Cubed root, we're trying to find a number 3 times. That gives us a number inside. Because the more times we multiply a number by itself, the bigger it's going to get. Which means when we try to find a cubed root of an index, the number inside that v is the index. All right, guys. When that number keeps getting bigger and bigger, the number is going to get smaller and smaller. Because we're going to have to multiply the number by itself more times. Now, previously you learned that the nth root of a is equal to a to the 1 over n. Now, it can also be said that the nth root of a to the x is equal to a to the x over n. We can rewrite radicals as these rational exponents. So these are the same thing. Also, we have this here, the real nth root. When we apply a root to an expression, to a number, we have these different properties. Go for it. Yes.
Can we paste our card for...
I don't have a card reader. But you have till Friday.
I do have till Friday?
Mm-hmm.
I know, I keep forgetting. Like, I just forgot.
So, when we take nth root, n is the number inside that v. We have 2 main setups if we're taking an even root or an odd root. Now, if the root is even and the number inside is greater than 0, we're going to have 1 real root. Or, you're welcome. No, we're sorry. We're going to have 2 real roots. We're going to have a positive and negative case if a is positive. If a is equal to 0, we're going to have 1 real root. And if a is 0 and we take an even root of it, it's going to be 0. Because 0 cannot be positive or negative, so we don't have 2, we just have 1. And if a is less than 0, we have a negative number. We have no real roots. Because both of the roots that we would have in that case are going to be complex, they're going to be imaginary, we don't have any real roots. So if we apply an even root to a number, and we try to apply this even root, find out what number times itself, an even number of times gives us the number inside the radical, we have 3 cases. If the number inside is negative, we have none. If it's 0, we have 1, it's just 0. And if it's greater than 0, we're going to have 2, so we have to put that plus or minus. Okay? Questions on applying an even root? We ready for odd roots? So if we apply an odd root to a number, and that number is greater than 0, we're going to have one real root. Okay, if the number is equal to 0, we're going to have one real root. And if the number is less than 0, we're going to have one real root. If we take an odd root, it doesn't matter if that number inside or what we're applying it to is positive, negative, or 0, we will always have one real root. When we take an odd root, we will always have one real solution, no matter what the number is. Questions on this here? So let's look at a few of these here, applying this indicated root. So we're trying to find out what the nth root of a is. And as we look at a, it tells us n is 3, and the number that we have inside is negative 216. So if we were to write this out, we would replace n with 3 and a with negative 216. Now the first thing I'd be looking at for this problem here is to see, are we taking an even root or an odd root? Here, is n even or odd? It's odd, so we have one of three cases we can have. If the number inside of it is positive, greater than 0, we're going to have one real root. If a is equal to 0, we're going to have one real root. If it's less than 0, if it's a negative number, we're going to have one real root. That's kind of the nice thing with taking an odd root, a cubed root, is that no matter what the number is inside, we will have one real root coming out of it. And there's two ways to go about it. One is to grab the graphing calculator or the 30xs, take the cubed root of negative 216. It helps if I actually type in 216 and not just 26. And it tells us that it is negative 6. Negative 6 to the third power is indeed negative 216. If we do this in the graphing calculator, we're going to have to hit math and scroll down to the cubed root, negative 216. It also tells us that it is indeed negative 6. So for the first one here, bless you, the indicated root, the nth root of a, the cubed root of negative 216 is negative 6. Yes. Any questions on A before we look at B? B, our n value is 4, and A is 81. Are we taking an even root or applying an even root or an odd root? Even. So we have one of three cases. If A is greater than 0, we have two real roots. If it's equal to 0, we have one real root. And if it's less than 0, we have no real roots. So here is A, the number that we've applied this to, positive, negative, or 0. It's positive. And since it's positive, it's telling us we're going to have two real roots. And we're trying to see here the fourth root of 81, two real roots. What number times itself 4 times is 81. Now we can do this in the calculator, second x root. 81 is 3. So what we're saying is that 3 to the fourth power should get us 81, and it does. Now, interestingly enough, it's saying positive or negative 3. We already saw the positive 3. Yes, sir. On the graphing calculator? Math, if you notice the one underneath the cubed root is x root, where x is just whatever number we want it to be. And then 3 to the fourth is indeed 81. Now it's saying that it's also negative 3, yes?
So I didn't the way you did it, but mine's coming out different.
So math?
Yeah, I did like that. I got like 1.3415.
So you still have that A and S. So A and S is taking the previous answer and applying it to. Now, interestingly enough, negative 3 to the fourth power is also 81, because a negative times itself an even number of times is going to become positive. Questions on either one of these here? Questions on how we did either one of these? We good with both of these so far? Let's look at another one. N is equal to 4, A is equal to 16. So our nth root of A would be the fourth root of 16. What times itself 4 times would be 16? 2. Now, since we do have an even root, we do have two cases. Because whatever this root is could be positive or negative. And then at this point, we can go 4. Root of 16 is 2, telling us that the fourth root of 16 is positive or negative 2. Now, we only need that plus or minus if we are applying this root to a number, if we are actually applying it to it. If it already has that fractional exponent, has that radical being applied, and we're just evaluating, we don't need the plus or minus. Questions on these so far? We ready for number 2? So for this here, we have square root of negative 49. Now we can put the 2 in the index if we want, but we don't have to, because an index of 2, a square root, that number is understood. We don't necessarily have to have it. And again, we're trying to find what real root gives us, if we apply this here, would be the square root of negative 49, and it is. Now, if we were actually just trying to find the square root of negative 49, it would be 7i, plus or minus 7i. But because it specifically wants real roots, well, there aren't any real roots, because 7i and negative 7i are complex. They're irrational. Or not irrational, they're just complex. Non-real solution. But because we have an even index, and the number inside is negative, we have no real roots. Because it's going to specifically on these here, it's asking for the real roots. Questions on this so far? Yes.
So if there's like negative inside the root bed, we don't need the plus or minus thing.
So for this one here, no. Because since it specifically asks for real roots, now yes, if we were just looking for what are the actual roots for this, it would be plus or minus 7i. But these here specifically, and especially on the homework for this here, are asking for real roots. What are the real solutions for this here? 7i and negative 7i are not real numbers. So since it tells us just specifically want the real values, we don't have any real values. Does that make sense? Let's look at number 3. It tells us n is 3 and a is negative 125. So what we're looking at is the cubed root of negative 125. Well, after that last problem, it might be helpful to look back and see if we do have any restrictions or how we need to apply this, but we're taking an odd root, yes? And odd roots are nice because the numbers that can come out of an odd root when we apply it to a number is either one real root, or one real root. We're going to get a number. Is negative 5. Negative 5 to the third is, indeed, negative 125. Questions on these so far? Questions on anything we've done so far? We're ready for the last one on this page. N is 5. A is 243. So we're taking an odd root, so we have one real solution no matter what that number is. And we need to see what times itself 5 times is 243. And that would be, we're saying 3. 3 to the 5th is indeed 243. Or we could have done 5 x root 243. And it does tell us that it is indeed 3. Questions on this here? Questions on anything we've done so far? Now, there are some ways we could have typed this in, because I could have typed it in as 243 to the 1/5, because the exponent attached to 243 is 1. Our index is 5. 3 to the 1/5 is still 3. Questions on any of those so far? Yes. Yes. Now, these next few, I want to work with us, and we're going to work through applying and rewriting these as fractional exponents and evaluating. Now, if we wanted to, and I just wanted to evaluate this expression, the square root of 5 to the 3rd, that's not too bad. We can go parentheses, square root of 5 to the 3rd power. We can just type it in as it is. It will tell us what it is. We don't have to do anything to it. But one thing I do want to look at is our properties. The nth root of a to the x is equal to a to the x over n. So even though it's not written, we know that that index with the 5 is indeed 2. So the square root of 5 can be rewritten as 5 to a fractional power. Now, because the 5 inside that radical does not have an exponent attached to it, have one written, it's understood to be 1. So the number on top of this fractional exponent is going to be 1. The number on bottom is the index, the number inside this v, so it is 2. So 5 to the 1/2 is going to be the same as the square root of 5. Questions on how we rewrote the square root of 5 as 5 to the 1/2? So the 2 and the v and the 1, yeah. And lastly, powers of powers multiply. So 1/2 times 3 would be 3/2. And we're saying this is equivalent to our square root of 5 cubed. There's an easy way to check that. 5 to the 3/2 does give us the exact same value. Now for this here, it doesn't help us much because it's not giving us a new way or easier way to calculate it. 1.80 or 180. But it can be a nicer way to be able to type these in and figure these out. Mm-hmm. Mm-hmm. Should. So let's look at the next one. The 4th root of 4 squared. So if we wanted to rewrite the 4th root of 4 as a fractional exponent, well, we know that the exponent, the x, the number that's going to go on top of this rational exponent is going to be 1. The n, the number on bottom, would be 4. So really we're saying that the 4th root of 4 is the same as 4 to the 1/4. Powers of powers multiply. 1/4 times 2 would be 2/4. And 2/4 is going to be reduced to 1/2, yes? Wait, we said 1/2 power is the same as the square root. We did it just a minute ago, yes? What's the square root of 4? 2. So 4 to the 1/2 should be 2. 4 to the 1/2. 4th root of 4 squared is still 2. So it's not as easy for us to see it in the general form and the starting form of the 4th root of 4 squared, but if we're able to rewrite it, we get it in a form that will simplify. Questions on these so far? Let's look at the next one, the cubed root of 9 squared. Well, we could rewrite the cubed root of 9 as 9 to the 1/3. Which is the same as 9 to the 2/3. Powers of powers multiply. And at this point here, we can plug it in. 9 to the 2/3 is 4.327. Questions on this here? Questions on anything we've done so far? 5th root of 10 to the 4th. So the 5th root of 10, if we rewrote it as a fractional exponent, it would be what? 10 to the 1/5. Powers of powers multiply. So 1/5 times 4 would be 4/5. Do we think this will be bigger than 1 or bigger than 10 or smaller than 10? Probably smaller. 6.3095, 6.310. But either way with these here, we can plug them in. And especially if it says evaluate and round to the 3rd decimal place, we can plug them in. We don't have to do them by hand. We don't have to simplify. Now, if it starts telling us we need it in simplest radical form, we are going to have to work these out. Questions on these so far? Eight to the 2/3. And especially these here, if we wanted to calculate them, I'd just plug them in. 8 to the 2/3 is 4. So if we plugged it in, it's telling us that this is indeed 4. But again, nth root of a to the x is equal to a to the x over n. Really what this is saying, 8 to the 2/3, if I rewrote it as a radical, a, the number inside, would indeed be 8. The index be on bottom, which is 3. And the power that is attached to 8 is 2. So really 8 to the 2/3 in radical form is saying the cubed root of 8 squared. Well, 8 squared is 64, so it's really telling us 64 to what power? What number to the 3rd is 64? And it would be 4. And there are other ways we can manipulate this and work it and get it to simplify out. 6 to the 5/2 is 88.182. 6 to the 5/2. 6 is going to be our a. The exponent attached to it is going to be 5, the number on top of that fraction. The index is the number on bottom is 2. We don't have to write that 2, but really we're looking at the square root of 6 to the 5th. Fortunately, I don't know what 6 to the 5th is off the top of my head. 7,776. So we're taking the square root this here, which would be 88.182. Questions on this here? Twelve to the 3/4. Do we think this is going to be bigger, smaller than, or equal to 12? Smaller. 12 to the 1st is going to be what? Anything to the 1st power is just the number itself, yes? So 12 to the 1st would be 12. 3/4, is that bigger than 1 or smaller than 1? Smaller, so we should expect the result to be smaller. If that fractional exponent is greater than 1, we should expect that number to be larger. 6.447. Ten to the 3/2. We should expect this number to be what? Bigger 3/2, 1.5. So it is indeed bigger. 31.623. Questions on what we've done here? Question on anything we've done so far? That's it. Now we will start getting into more of this with solving, and especially reducing these radicals where they don't reduce to a simple number or has to be approximated. We're going to have to leave them in simplest radical form, and we will go over how to do that and what's involved with that. But at this point, we can do most of this with just a calculator.